Hi, girls. Today we're going to go over some momentum questions. This is an addendum to previous videos that I did on momentum. So we are going to look at some other scenarios that involve 1D, 2D scenarios, some completely elastic, some inelastic. So here's the first question. First question is we have a 1 kilogram mass approaching a 2 kilogram mass. I guess we have to assume that in this question, the 2 kilogram mass is stationary. Let's pick a nice color here. We could use, let's pick this. So we're going to assume that this is stationary. Okay, so it's not moving initially. Okay, and we're going to figure out the final velocity for each mass. Now we're going to do two scenarios. One is where it's completely elastic, and the other one where it's completely inelastic. The difference between the two is in the completely elastic, the kinetic energy is also conserved, whereas in the inelastic scenario, it's not conserved because some of the energy goes into maybe causing the objects to maybe crumple a little bit. This energy lost in some other forms as heat, sound. Probably the big one is if two cars collide, they crumple. A lot of the energy goes into causing the cars to crumple, and therefore it's not conserved. So if it's completely elastic, we assume no energy is lost, which I guess would be hard to reproduce in nature. So let's look at the first one, completely elastic. Okay, so the idea here is the initial momentum is equal to the final momentum, but also the initial kinetic energy is equal to the final kinetic energy, right? Two big ideas. Okay, so let's take a look at it like, for example, a schematic. So imagine here your 1 kilogram mass, it's approaching, and this is your 2 kilogram mass. So I'm going to call this the 1 kilogram mass, and this is your 2 kilogram mass. And we're going to figure out what happens after collision, okay? So the initial momentum is the mass m1 times v1 plus m2 times v2. That's the initial momentum, and that's going to equal the final momentum. So m1 times v1 final plus m2 times v2 final. Okay, so let's put some numbers in. So initially, the momentum is, so we have 1 kilogram mass. Its speed is 2 meters per second east. So we're going to make east positive. Let's east, make that positive. Plus second mass, which is 2, but its speed is 0 initially. Velocity is 0, sorry. And that's going to equal the mass of the first object, which is 1, but its final velocity is unknown. So we're going to just say it's v1f plus the second mass, which is 2, times v2f, which we don't know. Okay, so this is going to give us 2 is equal to 1 v1f. I don't know why I'm writing 1. You don't need to write 1. I've written it, so we carry on. Okay, so here's one equation. All right, I'm going to call that equation 1. Okay, this is equation 1. Actually, let's rearrange it. We're going to rearrange and we're going to isolate for v1f. Okay, I'm going to say 2 minus 2 v2f is equal to v1f. This is 1 v1f, which is v1f. Okay, so there's an equation. Now, the reason why we're doing that is because we have to do substitution, as you'll see in a second, because we know that not only is the momentum conserved, but also the energy is conserved. So, which means that 1/2 mv squared, or m1v1 squared, plus 1/2 m2 v2 squared is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Okay, so first, let's just get rid of the half because it's quite annoying. So we're going to just eliminate the half. So we're going to cross them out. All right. And we are going to, let's change color. So we're going to have m1 v1 squared plus m2 v2 squared is equal to m1 v1 f squared plus m2 v2 f squared. Let's put our numbers in, okay? So m1 is 1 times its speed squared plus m2 times its speed squared, right, is equal to m1 times v1 f squared plus m2 times its speed squared. There's our equation. So it's going to give us 4 is equal to v1 f squared plus 2v2 f squared. Okay, so now what we're going to do is we are going to because we know what v1f is from over here. So we can put that into our equation. We can say that 4 is equal to v1f squared, but v1f is, from the previous example, v1f is 2 minus v2f. Now, there's your v1f, which has been substituted. Now that's squared plus 2v2f squared. Okay, so if we expand that out, 4 is equal to, if you expand this out, 4 minus 8v2f plus 4v2 squared plus the 2v2f squared. Okay, now this 4 is going to cancel out with this 4. It's going to give us 0. If we have vf squared and vf squared, so we can add those up. So we have minus v2f plus 6v2f squared. Okay, we can bring this over, say 8v2f is equal to 6v2f squared. We can get rid of the v2f, and then we can say 8 over 6 is equal to v2f. Or we could say v2f is equal to 1.33 meters per second. Okay. Now, let's see if actually that makes sense. So mass 1 is, there's mass 1, there's mass 2. So they're going to collide. V2 is the second object. It looks like it's positive because there's no negative sign. So it's saying that this object is going to move this way, which makes sense. If it's being hit by an object moving east, you would imagine that this object would then travel east. That makes a lot of sense. Now, what's going on with the V1? Okay, so we know V1F is equal to 2 minus 2V2F from over here. So if we sub in, so V1F is equal to 2 minus 2 times V2F, which is 1.33 meters per second. That's going to give us an answer of minus 0.66 meters per second. So it's saying after the collision, object 1 is actually going this way, which is reasonable. Makes sense. Now, if you were to test it out, you want to know if it's accurate. We know the initial momentum was 2. So if you plug in your values, so 1 times V1F, which is 1 times minus 0.66, plus 2 times 1.33, that adds up to 2, and therefore it works. Okay, now that's completely elastic. Let's look at completely inelastic, which is going to be a lot easier. Because in completely elastic scenarios, maybe we should make this color a little bit lighter. Okay, the initial momentum is equal to the final momentum, so that holds true. The energy is not conserved. But what's beautiful about this is that the initial momentum is defined as m1 v1 plus m2 v2. The final momentum is actually the sum of the masses because they stick together like two cars getting mangled and sticking together, times their final speed. So this one's going to be a lot easier to solve. We already know from the first section that the initial momentum was 2. So that's no different. Now, in this case, the mass is the sum of the two masses, so 1 plus 2, which is 3, and times your final speed, final velocity, sorry. Final velocity then would be 2 over 3, or 0.67 meters per second. So if object 1 hits object 2 in a completely inelastic scenario, and they get stuck together, then they would both travel in the direction of motion of object 1, which is east, but obviously at a slower speed as they're more massive. Okay, that is question 1. Now let's move on to question 2. Here's question 2. In question 2, we have an object approaching another object, but in this case, this is actually going to be two-dimensional. So we have an object, 1 kilogram mass. There's a 1 kilogram mass. Okay, 1 kilogram mass. Let me change the color, make it a little bit brighter. So there's my 1 kilogram mass object. All right, 1. Approaching a 2 kilogram mass object. Here's my 2 kilogram mass object. And it says the 1 kilogram mass object has a velocity of 2 meters per second east. And the 2 kilogram mass object has keep saying speed, has a velocity of 1.5 meters per second west. Okay, so in this case, 2 kilogram mass is actually moving. Okay, now the technique is the same. So from the previous question, we know that the momentum and the energy is conserved. Okay, so that would mean then that the initial momentum is m1 v1 plus m2 v2 is equal to m1 v1f plus m2 v2f. Okay, so m1 is 1, its initial velocity is 2, east is positive, plus the mass of 2, so second object has a mass of 2, but its velocity is 1.5 meters per second west, so it's going to be negative. It's going to be negative 1.5, okay? So that's going to equal m1 v1f, which is 1 times v1f, plus m2, 2 times v2f. Okay, so this simplifies to minus 1 is equal to v1f plus 2v2f. Okay, so we can rearrange and say v1f is equal to negative 1 minus 2v2f. Okay, so here's my equation. Let me make that a little bit nicer. Okay, so minus 1 minus 2v2f. Okay, now that's equation 1. The same thing as we talked about before, the energy is conserved. So we can say, and we know that from the previous example, if you remember, we factored out the half. So we could say m1 v1 squared plus m2 v2 squared is equal to m1 v1f squared plus m2 v2f squared. So in other words, we could say m1, which is 1, times v squared plus m2, which is 2, times v squared. So there's the mass of 1 in its velocity plus the mass of 2 in its velocity is equal to the mass of 1 times v1f squared plus the mass of 2 times v2f squared. So that's the same we did last time. All right. So this is 4. And this is 4.5. So 4 plus 4.5. Okay. So that's going to equal 1 v1f squared plus 2 v2f squared. So this is going to give us 8.5 is equal to v1f squared plus 2v2f squared. Okay, like we did last time, we are just going to substitute because we already know what v1f is. We have it over here, so we're just going to substitute that in now. Let's change the color. So we're going to say 8.5 is equal to v1f squared. The v1f squared is negative 1 minus 2v2f. Okay, that squared plus 2v2f squared. Okay, so we factor that out. So we got, or sorry, we expand it. Let's factor it out. It's going to give us 1 plus 4 v2f plus 4v2f squared plus 2v2f squared. Okay, so it's going to be 8.5 is equal to, let's move the 8.5 over. You can say 0 is equal to, move that over, it's negative. So negative 7.5 plus 1 is negative 7.5 plus 4 v2f plus 6 v2f squared. Hold on, I'm just checking something. Let me just pause this a second. Oh, damn it. Okay, I apologize for that. I realized that, oh, sorry, hold on. What's going on here? Okay, hold on, some technical difficulties. Enter full screen. Yeah, go back to screen sharing. Okay, where am I here? I'm right here. There. Okay, we're back. We are back. Sorry, I had a problem because I wrote down something wrong, which messed up a calculation. So I figured I'd pause the video and go back to it. So we are back, I believe. We are recording. You see, are we still recording? Yes, we are recording. Okay, good. Okay, so okay, so here we are. So we have this equation now. Obviously, in this case, we are going to need to put this into a quadratic. So I'm not going to bore you with the details of how to do that. You should know how to put that into a quadratic. Now, if you put that in a quadratic, we are going to get two possibilities for V2F. We are going to get, we are going to get V2F being either negative 1.96 or positive 0.63. Okay, this is where you got to use the big brain to figure out which of these two is the most likely answer. So V2F, let's look at V2F. Okay, so V2F is possibly going to have two velocities, negative 1.96 and positive 0.63. Okay, so its initial velocity is 1.53, right? And it's going west. So that's a velocity of negative 1.5 to the west. Now, it's colliding with something that's moving in the opposite direction. So would it make sense that after the collision, it would be faster going in that direction? No, it doesn't make any sense at all. Is it possible that it's going in the other direction? Yes, it is. So this is the answer that makes sense. So this is the answer we are going to take. So we are going to now plug that in to figure out what V1F is. So from before, V1F is negative 1 minus 2 V2F. So if we plug that in, minus 1 minus 2 times 0.63, it's going to give us a velocity of minus 2.26. And for object 1 is traveling west at 2.26 meters per second, which makes sense because it is colliding with a bigger object. Therefore, after collision, probably going to be going west. Okay. All right, that's a lot of work. Now, the inelastic scenario is definitely a lot easier. If you remember from before, the inelastic scenario, the initial momentum equals the final momentum. We already know what the initial momentum is, right? We worked it out from before. The initial momentum is 1 from over here, right? And that equals the final momentum. But these two objects are completely inelastic, they're stuck together. So that's the combined mass of the two objects, which we know is 3 times the final speed. So I keep saying speed, final velocity. So that's going to give us a final velocity of 1 over 3 or 0.33 meters per second. Was that? Sorry, the initial momentum was -1. Kind of, yeah, I drew over it so I couldn't see it. Yeah, that makes more sense. It didn't make sense that it was positive because this object has a bigger momentum. This momentum of this object is 2 times 1.5, which is 3 to the west, and this is 2 to the east. So the momentum is pointing, you add those up, points west. So yeah, that's negative. Sorry about that. So the velocity is negative 0.33 meters per second. Always make sure that the answers make sense when you're doing these types of questions. Okay, let's move on to the next question. Okay, so here we have a truck traveling east, colliding with a car traveling north, and they get stuck together. Beautiful. These are a little bit easier to deal with. Now, this is two-dimensional. So we have a truck going east, okay? And it hits a car going north. So eventually they get stuck together in some heap of mess. And they're probably going to go off in some northeast direction, which makes a lot of sense. Now, if we have to, we got to look at this as x and y independently. So let's look at the momentum in the x direction, okay? So the momentum in the x direction, we know initial is equal to final. So the initial momentum in the x direction is the mass of the truck. So m1 times the speed of the truck plus the mass of the car times the speed of the car is equal to the sum of the masses times their final velocity. Okay, that's easy to do, right? M1 is 2000, V1 is 20, M2 is 1200, but V2 is 0, so that's going to give us 0. Is going to equal the sum of the masses, which is, in this case, 2000 plus 1200 is 3200, times VF. Okay, so that's 0. If you solve for VF, VF will be 12.5 meters per second east. Now, we do the exact same thing for the momentum in the y direction, okay? In the y direction, the truck has a mass of 2,000, but its velocity is 0. The car has a mass of 1,200, but its velocity in the y direction is 30. And the combined mass is the same. And the final velocity in the y direction is the unknown. So that's 0. Now, if we solve for VF, in this case, we get 11.3 meters per second going north. Now, what do we have? We have components here. We have velocity going east, 12.5. We have velocity going north, 11.3. So what we can do now is we could solve for the actual velocity as the sum of the squares. That will give us a velocity of 16.9 meters per second. And we can solve for the angle using inverse tan of 11.3 over 12.5. And that's going to give us an angle of about 42 degrees. Therefore, the final velocity will be 16.9 meters per second. east, 42 degrees north. Okay, there you go. All right, those completely inelastic scenarios are a lot easier to deal with. Okay, let's look at the next question. The next question is two-dimensional, but completely elastic. But actually, because it's two-dimensional, we're going to use a different trick to be able to solve the answer to this question. So we have a cue ball traveling. So here's my cue ball. We call that ball A. Okay, it's traveling. Actually, the cue ball should be black, but you want to see it traveling and hitting another ball. Okay, call that ball B. Okay. Now what happens is the after the collision, ball B goes this way, and ball A goes that way. Okay. The angle that ball A makes after the collision is, it says west 20 degrees north, so the angle is 20 degrees. And whereas B makes an angle of west 15 degrees south, so that angle is going to be 15 degrees. Okay. Now, B is stationary, A is the one that's moving. All right, so what we're going to do is we're going to look at these two scenarios, X and Y, independently, like we did with the previous question with the truck. So let's look at the initial momentum in the X direction, okay? Initially, it's the momentum of A plus the momentum of B, right? Okay, well, momentum of A is its mass, so 0.3 times its velocity, which is 2 meters per second west. So I'm going to make that a negative value, plus the momentum of B. B is stationary, so we know when something is stationary, its momentum is 0, right? So its initial momentum is negative 0.6 in the X direction. Okay, all right, that's good. Now, we know that that equals the final momentum. So the initial momentum is negative 0.6, and that's going to equal the final momentum. Okay, so what's the final momentum? Well, we know the angle. So what we could say is that the mass of ball A, I'm going to say the mass of ball A times its velocity, its final velocity of ball A, but in that X direction, right? Plus the mass of ball B times the final velocity of B, but again, in that X direction, that equals negative 0.6, right? Okay, so negative 0.6 is equal to ball A. Ball A is a mass of 0.3 times its velocity in that X direction. So what would that be? Well, that would be, we could say its final velocity times cosine of 20, right? We can do the same thing for V and say that its mass, which is 0.35, slightly heavier for some reason, times the final velocity of V times cosine of 15. Okay, that's going to equal negative 0.6, right? Now, what we can do here, we can make this, we can simplify this, and we could say that negative 0.6 is equal to 0.3 times cosine 20 is 0.28 VFA plus 0.35 times cosine 15 is 0.38 VFB. Sorry, I skipped a step here. That's VF. Yeah, I skipped a step. Yeah, back up here. I already did a substitution. Sorry. Let's back up a little bit. Let's back up. Hold on. Let me fix this. Let me back up. I'm reading my notes here, and I already did a substitution. So let me show you the other equation before we move on. Then let's look at the y direction. Okay. I'm gonna follow my notes that I made here. And I spent time on. So let me follow my notes. I'm gonna say in the y direction, we have the initial momentum is 0 because it's not going, there's no ball moving north or south initially, right? So we know the initial momentum is 0. Now, what does that equal? It's going to equal the mass 0.3 of ball A times the final velocity of ball A, but the sine of that angle, right? It's this component, okay? Minus the mass of ball B times its velocity, but in this direction, which is that velocity times sine 15. Okay, so what I'm going to do is I'm going to rearrange, and I'm going to solve for VFB here, and then I'm going to put it in here, which is what caused me the grief before. So what I could say then is 0.35 VFB sine 15 is equal to 0.3 VFA sine 20. And then I can solve for VFB and say that, well, not solve for VFB, but simplify for VFB and say that VFB is equal to 0.3 VFA sine 20 over 0.35 sine 15. So that's going to give me VFB is equal to 1.13 VFA. Now I'm going to go back to this step, which I was doing before, but I had my notes already did that substitution. So now what I'm going to do is I'm going to go back to this equation and say, okay, so negative 0.6 is equal to 0.3 times cosine 20 times VFA is 0.28 VFA. Okay, plus 0.35 times VFB, which we know what VFB is. VFB is 1.13 VFA times cosine 15. Okay, and that's going to give us 0.6 is equal to 0.28 VFA plus, so 0.35 times 1.13 times cosine 15. Now I'm going to double check to make sure that I actually did this substitution, because it would be, this attorney would say, embarrassing. So let me just double check this. So 0.35 times 1.13 times cosine of 15 equals 0.38. That's right. Okay, so 0.38 VFA. Okay, now we can put the VFAs together. So we got 0.68 VFA and, sorry, 0.28 VFA. Can't read my own writing. Plus 0.38 VFA is going to give us 0.66 VFA. That means VFA is equal to negative 0.91 meters per second. Okay, so now we can plug that in and solve for VFB. We can say that VFB is 1.13 VFA, where VFA is negative 0.91. VFB then is negative 1.03 meters per second. So ball A is traveling at 0.9. Actually, let me use the same color. So ball B is traveling at 1.03 meters per second. And ball A, I think I used this color, is traveling at 0.91 meters per second. Okay, I'm going to pause this video for a second because I have something on the stove and I don't want to burn down my house. So let me just pause this and I'll be right back. Okay, I'm back, still alive. House has not been burned down. Okay, let's move on to the next question. All right, here we go. Next question. A cannon firing a cannonball. All right, here we go. We have a 400 kilogram cannon firing a 2 kilogram cannonball with a velocity of 50 meters per second. We're going to figure out the recoil velocity. Okay, so this is no different than momentum this is no different than what we're talking about, where the initial momentum is equal to the final momentum, right? So in this case here, we know the initial momentum is equal to the final momentum. Let me switch colors, not be a little bit too dark. Okay, that's been true of all the scenarios we've looked at, whether they're collisions or explosions in this case. So the initial momentum is 0. Why? Why is it 0? Because the cannon and the cannonball are before explosion, they're not moving. So initially, the momentum is 0. Now, after the explosion, the cannonball is traveling at 50 meters per second. We'll look at this picture. Say it's going to the left. We'll make the left negative. Okay, and we'll make the right. We'll say that one is positive. So we could say the final momentum is the mass of the cannonball, which is 2, times its velocity, which is to the left. So I'm going to make that negative 50, plus the mass of the cannon itself, which is 400, times its recoil velocity, which we don't know what it is. Okay, so that's going to give us 0 equals minus 100 plus 400 VF. So we can move this over to the side. Going to give us 100 is equal to 400 VF. So VF is equal to 100 over 400, which is 1 over 4, which is 0.25 meters per second. So if it fires the cannonball at that speed, this cannon will move back at a rate of 0.25 meters per second after that explosion. Okay, next question. There we go. A disk that explodes. Okay, so whether it's collision or explosion, momentum is conserved. So the concepts are all the same. So let's draw this out. Let's say we have a disk. So here's my disk, okay? And it says that one fragment flies off east. So we're going to say that, imagine like it breaks up into 3 fragments. One fragment flies off east, and it has a mass of 1.1 kilograms, okay? That's fragment 1. Now another fragment flies off southwest. I'm going to do a piece of the disk goes this way, and it has a mass of about 0.9 kilograms, and it's going off southwest, which would make sense that the last fragment is going like some northwest direction based on this this drawing, and that piece is 1.2 kilogram. Okay, and that's fragment 3. Okay, so here's what we know. We know that in both the x and the y direction, the initial momentum is 0, right? So whether it's the y or the x direction, we know the initial momentum is 0. So let's look at the x direction. We know the initial momentum is 0, so therefore the final momentum should be 0. We have fragment 1 that's traveling east. Its mass is 1.1 kilograms. Momentum is m times v, and it's traveling 40 meters per second east. That's one fragment. Fragment 2 is traveling southwest. So we're going to need this component, right? Because we're looking at the x component. So we could say that fragment 2, which has a mass of 0.9 kilograms, is traveling at a speed of, velocity of 35 meters per second. But because we want, let's say we're using, let's say that's the angle, right? When it's 45 degrees, doesn't really matter, but we want this component. So we can say times sine 45. But here's the thing. Which way is that pointing? That's pointing this way. So obviously this is not going to be positive. This is actually going to be negative, right? It's going the opposite way. Plus fragment 3, which is 1.2 times its unknown velocity. Call that v3f, okay? Now, if we look at the y direction, okay, we have fragment 1 is not traveling in the y direction, so its momentum is 0. Fragment 2 is traveling south, so that's going to be negative. And with its momentum will be its mass times 35 times cosine 45. And then fragment 3 is again its mass times its velocity in that y direction. Okay, so now what we can do is we can solve for each one. So let's solve for the x component. So the x component is going to be 0 equals 1.1 times 40 is 44. 0.9 times 35 times sine 45 is 22.3. And that's plus 1.2 v3f. Okay, so if we simplify, 0 is equal to 21.7 plus 1.2 v3f. So if we rearrange and solve for v3f, v3f is going to give us an answer of negative 18.1 meters per second. Okay, and again, this is for the x, right? Now, if we do the same thing for y, change the color. We know for y, it's 0 is equal to 0 minus 22.3. It's the same as this because it's 45 degrees. Plus 1.2 v3f. We solve for v3f, we're going to get an answer of 18.6 meters per second. So now that would be our y component. So now we have the velocity in the x, and we have the velocity in the y. We can put it together. We know, let's finish it over here. Okay. We know that in the x direction, it's going west, which is kind of what we predicted. And the y direction is going north, which is kind of what we predicted. And that is 18.1, and that is 18.6. So if we solve for this, we're going to get an answer of about 26 meters per second. We should include an angle. So if we do inverse tan of 18.6 over 18.1, we get an angle of about 46 degrees. Therefore, the final velocity for object 3 would be about 26 meters per second. We can say west 46 degrees north. Although my north looks exactly like my west. Let me fix that. West 46 degrees north. Okay, one last question, and then the marathon is over. Now this question is different because it's actually a question about impulse. So what is impulse? Impulse is actually referred to as the change in momentum. So change in momentum is defined as delta P. Let's change this color again. Keep getting this color in the Y. That's the change in momentum, delta P. So that is going to equal then m delta v. This is a change in momentum. It's either because the mass or the velocity is changing. Most likely the velocity. Now, if you remember from grade 11, A is delta V over T. So we could rearrange and say that delta P is equal to M times delta V, where delta V is basically A times T. Okay, now delta P then is equal to MA times T. Well, what's MA? MA from last year is force times T. So change of momentum for the impulse is a function of force times time. So we're going to look at an example here of a home run hit on the 29th of March, 2018. Oh my God, that was like almost exactly 2 years ago. No baseball yet, coronavirus. So in this scenario, Giancarlo Stanton hit a home run, and the initial speed of the ball was 91.7 miles per hour. Yes, our American friends like it in miles per hour. So just so you understand, 1 mile per hour is about 0.447 meters per second. So if we can convert this, that would be nice. So this is about 41 meters per second. And this is about 91.7 meters. Sorry, not 90, sorry, it's about 52 meters, 52.5 meters per second. Now, if the ball is coming one way, and the bat hits it, and the ball goes the exact opposite way, we're going to assume it's the exact opposite way, okay, for simplicity's sake, then what we could say is that the initial direction, maybe we'll make that negative, and then the final direction will make it positive. They have to have the opposite signs because they're moving in the opposite direction. So if we set up an equation where delta P is equal to F times T, now delta P is mass times the change in velocity is equal to force times time. There's your impulse, right? We could say that the mass of the ball is 0.145 kilograms. The change in velocity is, this is the initial velocity, and this is the final velocity. So we could say 52.5 minus negative 41, which makes positive 41, is equal to F times T. Now we have the time. In this equation, it says that the contact is 1 millisecond, which seems a little fast, but let's go with it. 1 millisecond is exactly 0.001 seconds. So that's the only unit I put in. I didn't put any other units in, but it's the only unit I put in. So in this case, the force is going to be a whopping 13,558 newtons, around the up. Which, by the way, would like just obliterate someone's skull. Just saying. Okay, that's it, ladies. Thank you. Have a good day.